Monoidal categories and their representations, Lecture 9, Drinfeld center. Let us start with a motivational detour into the notions of a center of a ring and a center of a category. Let R be a unital and associative ring. Recall that the center Z of R, of the ring R, consists of all elements in R which commute with all other elements in R. So an element Z in R belongs to the center if and only if ZR is equal to RZ for all R in R. Note that Z of R is a commutative and unital subring of R, because the identity obviously belongs to the center. The first property of the center is that for any R module M and any element Z in the center of R, the action of Z on M is an endomorphism of this R module. And this, of course, follows directly from the fact that Z commutes with all elements in R. In particular, this defines a ring homomorphism from the center of R to the ring of all endomorphisms of M. Property 2, we have a natural isomorphism between the center of R and the endomorphism ring of the RR bimodule R. Proof: for injectivity, we can simply evaluate this isomorphism at the identity element. For surjectivity, let little z be the image of the identity element under some endomorphism. Of course, this image completely determines the endomorphism because the regular bimodule R is generated by the identity element as a bimodule. And then it is easy to check that this Z defines a bimodule endomorphism if and only if Z belongs to the center of R. Next, let us discuss the notion of the center of a category. Let C be a category. Definition: the center of the category C is defined as the endomorphism monoid of the identity endofunctor of C. In other words, the center of C is given by all collections xi, so we take an object in C and we associate to it a morphism in C, which satisfies the following condition. So first of all, xi of x should be an endomorphism of x, and then for all morphisms f from x to y, the following diagram should commute. If we start with x, we can first go by f and then by xi y, and this should be the same as if we first go by xi x and then by f. For example, consider a monoid M with binary operation star and the identity E. Having such a monoid, we can construct a category Cm with one object, such that the endomorphism monoid of this object is exactly M, with this operation and with this identity. Then the center of this category is exactly the center of the monoid M. In relation to modules over rings, we have the following property. So let R be a unital and associative ring. Proposition: the center of R is isomorphic to the center of the category of all R modules. Proof: so the center of the category is the endomorphism thingy of the identity functor. For the category of all R modules, we know that the identity functor is isomorphic to tensoring with a regular RR bimodule R. And we have seen that the center of R is isomorphic to the endomorphism ring of this regular RR bimodule. And this proves our proposition. A nice corollary from this proposition is that the center of R is isomorphic to the center of the category of all finitely generated R modules. Of course, we can restrict natural transformations of the identity functor from all modules to finitely generated modules, and this map is an isomorphism when restricted to the free R module R of rank 1, and this is a finitely generated R module. Remark: given an R module M and a central element Z in R, the endomorphism of M, given by the action of the central element Z, can be alternatively described as the evaluation at M of the endomorphism of the identity endofunctor of R mod, which corresponds to this central element Z. Please note that not all endomorphisms of M have such a form, that is, that they are given by the action of the central element in general. Now we can define the notion of a Drinfeld center. This will be a long definition, and we start with objects in the Drinfeld center. Let C be a monoidal category. Definition: the center or the Drinfeld center of C, usually denoted Z of C, is the monoidal category, which is defined as follows. So we start with the definition of the objects in the Drinfeld center. The objects in the Drinfeld center are all pairs x, phi, where x is an object of C, and phi is a natural transformations of endofunctors of C, where the first endofunctor is given by tensoring with x on the left, and the second endofunctor is given by tensoring with x on the right. So phi should be a natural transformations between these endofunctors, and moreover it should be an isomorphism, so an isomorphic natural transformation. Additionally, the following diagram should commute. So this is a coherence condition on phi. So if we start from x tensor y tensor z, we can apply the associator to go to x tensor y tensor z. Then we can apply phi to go to y tensor z tensor x. And then we can apply the associator to go to y tensor z tensor x. Alternatively, starting from x tensor y tensor z, we can apply phi in the first bracket to go to y tensor x tensor z. Then we can apply the associator to go to y tensor x tensor z. And now we can again apply phi in the bracket to go to y tensor z tensor x. This gives us two ways in this diagram, and they should coincide. So this diagram should commute. Now let us define morphisms in the Drinfeld center. Given two objects in the Drinfeld center, x, phi and y, psi, a morphism in the Drinfeld center from the first object to the second object is a morphism f from x to y in C, such that the following diagram commutes for all z in C. When we start from x tensor z, we can apply phi to go to z tensor x, and then we can apply identity tensor f to go to z tensor y. Alternatively, starting from x tensor z, we can apply f tensor identity and go to y tensor z, and then we apply psi to go to z tensor y. So these two ways should be equal, so this diagram should commute. So we define composition of morphisms in the Drinfeld center using the composition in C, and we define the identity morphisms in the Drinfeld center as given by the identity morphisms in C. And it's clear, so we now have defined objects and morphisms, it is clear that this defines a category. So by now we have defined this Drinfeld center as a category. So now let us define it as a monoidal category, so let us define the tensor product and the unit. Given two objects, x, phi and y, psi in the Drinfeld center, we define their tensor product, x, y, tensor y, psi, as the object x tensor with y, epsilon, where epsilon is a morphism defined using the following commutative diagram. So this is a hexagonal diagram, and in this diagram all maps are isomorphisms, so we can invert them if necessary in order to uniquely define epsilon. So if we have x tensor y and then tensor with z, so we define epsilon z, it should go to z tensor x tensor y. And now we will go from the first object to the second one via a much longer path. First of all, we can use alpha to go to x tensor y tensor z, and then use psi here in the bracket to go to x tensor z tensor y. To this object we can come from x tensor z tensor y using alpha, so we can invert it if you wish. And here we have x tensor z in the bracket, to which we can apply phi to go to z tensor x tensor y. And now from this object we can go to z tensor x tensor y using alpha. This defines the map epsilon for the pair x tensor y epsilon. And the unit object in the Drinfeld center is defined as a pair the identity object, comma, rho inverse lambda. So lambda is a map from I tensor z to z, and rho is a map from z tensor I to z for any z in C. And so if we take the composition, we get a map from I tensor Z to Z tensor I. Of course, we have to invert rho. So this defines the tensor product and the unit. Next, let us define the left unitor in the Drinfeld center. And the claim is that the left unitor lambda in category C is actually a morphism in the Drinfeld center from the tensor product of I, rho inverse lambda with x, phi to x, phi. To prove this, we consider the following big diagram. So we have x, phi in the Drinfeld center, and U is an object of C. So we consider the following diagram. So we have the object I tensor U tensor X. To this object, we can use lambda to go to U tensor X, or we can use alpha to go to I tensor U tensor X. From I tensor U tensor X, we can use lambda to go to U tensor X, the same as here. Then we have the object I tensor X tensor U, and here we can use phi in the bracket to go to I tensor U tensor X, or we can use lambda to go to X tensor U. From X tensor U, we can use phi to go to U tensor X. And here we have the object I tensor X tensor U. We can use alpha to go to I tensor X tensor U, or we can use lambda in the bracket to go to X tensor U. And here in this part, we have U tensor I tensor X. Using rho, we can go to U tensor X. Using alpha, we can go to U tensor I tensor X. And here, using the identity tensor lambda, we can go to U tensor X. So we have such a diagram. And again, note that all maps in this diagram are isomorphisms, so they can be inverted if necessary. So in this diagram, we have the following. The southwest triangle commutes by a proposition from lecture 2. So this is the southwest triangle, and this is exactly the statement of a proposition in lecture 2. Next, the trapezoid above this southwest triangle commutes by the naturality of lambda. So this is the trapezoid. We have lambda here, phi here, and identity tensor phi here. So this is exactly the naturality of lambda. Next, we have a rhombus in the middle, which commutes by the same proposition from lecture 2 as above. This is a rhombus in the middle, and one of the sides is actually the identity. So in reality, we have a triangle, and this is a very similar triangle to the one which we have here. So it commutes for the same reason. And finally, this quadrangle here, which looks like a triangle, but is in reality a quadrangle on the picture, but since it's the identity here, so it's really a triangle. So this triangle commutes by one of the monoidality axioms. So the diagram commutes. And now if you look at the perimeter of the diagram, this perimeter says exactly that lambda is a morphism from this tensor product to x, phi. So this establishes how we have left unitors in the Drinfeld center. Similarly, the associator from C is a morphism in the Drinfeld center, and one can prove this similarly, but using a slightly bigger diagram. And also the right unitor lifts from C to the Drinfeld center. And then one can check that this structure which we have, tensor product, associator, and the two unitors, makes the Drinfeld center into a monoidal category. So the monoidal axioms for the Drinfeld center can be lifted from the monoidal axioms for the monoidal category C. Okay, so we have a monoidal category and its Drinfeld center, which is also a monoidal category. What kind of other structure can be lifted from C to the Drinfeld center? And the first thing which we will discuss is adjunctions. Let C be a monoidal category, and let x, y be an adjoint pair of objects in C. Let eta and epsilon be the corresponding adjunction morphisms. So eta is the unit from the identity to yx, and epsilon is a co-unit from xy to the identity. Assume that we have an object x, phi in the Drinfeld center. So we want to construct an adjoint object to this object x, phi. So define psi, and psi will be a natural isomorphism from y tensor with something to something tensor y. So we define this psi via its evaluation at some object u in C as decomposition in the following very long diagram. So we start from y tensor u. To this element, we can go by row from y tensor u tensor the identity. Here, we can use eta to the identity to go to y tensor u tensor y tensor x. To this element, we can arrive using alpha from the element y tensor u, tensor y, and then tensor x. And here, we can use phi or phi inverse to relate this element to the element x tensor y tensor u tensor y. Again, we use associator to move the outer brackets, and then the associator one again to move the brackets inside the outer brackets. And now we have x tensor y here, to which we can apply the epsilon, and then we have the identity here, so we can apply lambda. And finally, we arrive at u tensor y, so y has moved on the other side. And not all maps in this diagram are isomorphisms, but alphas and phis are, and so they can be inverted, and rho is an isomorphism, so we can read this diagram from the first object to the last object. And this defines a map from y tensor u to u tensor y. And then one can check that the pair y comma psi is an object in the Drinfeld center. Moreover, the pair consisting of the objects x comma phi and y comma psi is actually an adjoint pair of objects. In other words, we can lift adjunctions from C to the Drinfeld center of C. In particular, if C is a rigid category, then its Drinfeld center is also a rigid category. Also note that we have the obvious forgetful functor from the Drinfeld center to the original category C, which sends the pair x comma phi simply to x. And directly from the definition, it follows that this functor is a monoidal functor because it's forgetful functor. It's a very easy exercise to see that sending x comma phi to x comma phi inverse is a monoidal equivalence from the monoidal category C to the opposite monoidal category C, op. One of the most interesting properties of the Drinfeld center is that, compared to the original category C, the Drinfeld center has a piece of extra structure. It has braiding. So let's see be a monoidal category. The claim, the Drinfeld center of C is a braided monoidal category where, for two objects x comma phi and y comma psi in the Drinfeld center, the corresponding braiding sigma for this pair of objects is given by evaluating phi at the object y. Proof? Let us first show that phi evaluated to y is a morphism in the Drinfeld center from the tensor product of x comma phi and y comma psi to the tensor product of y comma psi and x comma phi. For this, we consider the following big diagram. So we start from x tensor y tensor u, and using alpha, we can go to x tensor y tensor u. Using psi in the bracket, we can go to x tensor u tensor y. To here, we can come using alpha from x tensor u tensor y. Using phi in the bracket, we can go to u tensor x tensor y. From here, using alpha, we can go to u tensor x tensor y. And from here, using phi in the bracket, we can go to u tensor y tensor x. Alternatively, starting from x tensor y tensor u and using phi, we can go to y tensor x tensor u. Using the associator, we go to y tensor x tensor u. Using phi in the bracket, we go to y tensor u tensor x. And to here, we can come using the associator from y tensor u tensor x. So here we can use psi in the bracket to go to u tensor y tensor x, and using the associator, we arrive to u tensor y tensor x. Also know that we can use phi to go from x tensor y tensor u to y tensor u tensor x, and from x tensor u tensor y to u tensor y tensor x. So we have such a big diagram. So here we have two hexagons and one parallelogram. So in this diagram, the two hexagons commute by the axioms for the objects in the Drinfeld center. So we have alpha phi alpha is equal to 5 tensor identity alpha identity tensor phi. And similarly here. So these two hexagons commute using the axiom for an object in the Drinfeld center. And the middle parallelogram here, it commutes because of the naturality of phi. So we have 5 here, identity tensor psi and psi tensor identity. So the middle parallelogram commutes by the naturality of phi, hence the whole diagram commutes. And again, reading the perimeter of this diagram gives us exactly the claim that phi evaluated at y is a morphism from this tensor product to this tensor product, which was necessary. Finally, the hexagonal Braiding diagram for sigma defined in this way follows directly from the hexagonal axiom for objects in the Drinfeld center. Let us consider some examples of Drinfeld center. We start with vector spaces. Let K be a field, then the Drinfeld center of the category K mod is monoidally equivalent to K mod. Indeed, consider an object v, phi in the Drinfeld center of K mod. This means that phi, evaluated at some vector space X, is an isomorphism from v tensor X to X tensor v. Since tensor product over K is biadditive and phi is natural in X, we can uniquely determine phi but by its value at the one-dimensional vector space K. So phi is uniquely determined by phi K. So we have an isomorphism phi K from V tensor over Kk to K tensor over Kv. And this can be naturally identified with a linear operator on V. And then, using the hexagon axiom, we actually see that one pass of the hexagon axiom has phi k once and another pass has it twice. So we have that phi k should be an idempotent and hence an identity because it's an isomorphism. In particular, it means that the pair v, phi is defined uniquely up to isomorphism for each v. And of course, if we take the identity object, we have the corresponding Drinfeld center element given by the pair the identity object, rho inverse lambda. This always exists. And if we get the direct sum of the dimension of v copies of this identity object, rho inverse lambda, we get up to isomorphism our unique element v, phi. And so from this it follows that the forgetful monoidal functor from the Drinfeld center to K mod is actually an equivalence. Here is another example. Let's consider modules over the cyclic group of order 2. So consider the cyclic group G of order 2 consisting of two elements, the identity E and the element S. Of course, S square is the identity then. Let us work over the field C of complex numbers. Then our group has two simple modules. The trivial module C-triv, on which the element S acts as the identity, and the sign module C-sign, on which the element S acts as -1. For any of these two modules, denoted V, and any element W in our group, consider the pair V, phi W, where phi W is a natural isomorphism from V tensor with something to something tensor with V, defined as follows. If we evaluate phi W at some vector space X and apply it to the element V tensor X, then we should get W applied to X tensor V. And it is very easy to check that this element belongs to the Drinfeld center of G mod. It is also very easy to see that pairwise different elements of this form, V, phi W, as above, are not isomorphic. Indeed, if V is not isomorphic to W, then V, phi W and W, phi U are not isomorphic because there are no maps from V to W in G mod by Schur's lemma. At the same time, if W and U are different elements in G, then V, phi W and V, phi U are not isomorphic if we compare what happens if we evaluate these pairs at the sign module C sign. So one of them will come up with a minus sign because one of these two elements, W or U, is the element S, and the other one is the element E. And in this formula, we have this element applied to X, so one of them will act as the identity and the other one as minus identity. And this will lead to the fact that there is no isomorphism between these two objects in the Drinfeld center. From this it follows that we have four different objects in the Drinfeld center: the trivial module with phi e, the trivial module with phi s, the sign module with phi e, and the sign module with phi s. And one can show that these are exactly the simple objects in the Drinfeld center. In particular, we see that the Drinfeld center has four simple objects, while the original category has two, so it's twice as big as the original category. And to explain this, I just mentioned that there is a notion of a Drinfeld double related to the whole story. Finally, let us discuss how we can think of Drinfeld center in terms of the endomorphism category of the identity functor. Let C be a monoidal category. Consider the bicategory C star with one object star, and such that the endomorphism monoidal category of this object is equal to C as a monoidal category. An endomorphism of the identity pseudofunctor of this bicategory C star is given by a choice of an object in C and the natural isomorphism from tensoring with this object on the left to tensoring with this object on the right, which satisfies exactly the same coherence conditions which we see in the definition of the Drinfeld center. And this realizes Drinfeld center as the endomorphism category of the identity functor, which makes one more parallel with this property that the center of the ring is isomorphic to the center of the category of the modules over that ring. Okay, some questions and problems at the end. Question 1. What is the center of the category of finite sets? Question 2. Check with all details that the associator is a morphism in the Drinfeld center. Question 3. Check with all details that the right unitor is a morphism in the Drinfeld center. Question 4. Check with full details that the pair y, psi is an object in the Drinfeld center in our discussion of lifting of adjunctions. And question 5. Check with all details that the pair consisting of the object x, phi and y, psi in the Drinfeld center, so this pair is an adjoint pair of objects. Again, this refers to our discussion of lifting of adjunctions. Thank you very much and see you next time.